There's often requirements to manage our network devices, like our routers and switches and firewalls, and many times that remote access is going to be in the form of getting access to a command line interface where we can type in the text to either find out the status of that system or to make configuration changes or both. And in this, take a look at two options we can use for that remote access to the command line interface. One of those options is Telnet, and the other option is SSH. And with those two primary methods being Telnet and SSH, Telnet is a really bad idea in a production network. And that's because the Telnet session, all the packets that are sent back and forth, they are not protected or encrypted or hidden in any way. So unless we're using something else on top of that to protect a Telnet session like a VPN tunnel in addition to the Telnet, Telnet is a bad idea. So if we're not using Telnet for command line access, what are we using? And the answer is SSH, the secure shell. And with secure shell, it's going to use encryption as it sends those packets back and forth between the device we're managing and the device we're initiating that SSH session from. So for a demonstration, let's go ahead and use router 1 as a client, and we'll establish some connections over to router 3, who's acting as a server. So we'll start off with Telnet. We'll Telnet to the IP address of 10.23.0.3, which is R3's IP address on its gig 1/0 interface. And then we'll close that connection, and then we'll try it again with SSH. And what I thought would be fun too is if we capture the packets in the background and see the huge difference regarding Telnet having no encryption whatsoever and sending all the information back and forth in plain text versus SSH, which does a great job of encryption. So here from the console on router 1, let's go ahead and just do a Telnet to 10.23.0.3. We'll press enter. It's asking us to authenticate. We'll authenticate as the username called learner, and then we'll go ahead and put in the password. So here we'll go ahead and type in exit to exit our session from R3, and now we're back to the command line interface on router 1. Next, let's go and do a SSH connection over to the same router, router 3, and the syntax here on the Cisco router is SSH space -L to indicate who we want to log in as. We'll put the username of learner and then the IP address of the SSH destination we're trying to reach, which is router 3, and we'll press enter. Once again, it's asking me for a password. I'll go ahead and supply that and press enter. And once again, we're connected. If we use the command show space SSH, it shows us the information regarding the current SSH sessions which are in place, including some hashing algorithms and encryption algorithms. And they've got those set up for both directions, for traffic going to the SSH server, R3 in this case, as well as the return traffic going from R3 back over to R1. So next, let's take a look at the packet details from a protocol analyzer regarding each of those sessions. So here's the Telnet one. So if we go to the first of the three-way handshake for that Telnet session, which is right here, we could right-click on that first packet, and then in Wireshark, from the drop-down, we could go ahead and hover over follow, and then select TCP stream. And that'll show us the entire TCP conversation that was captured. So the red represents packets going from the client, the blue represents the packets coming from the server. And so here they're doubled up because as we type a character in Telnet, that's being reflected back to us on our screen coming back from the Telnet server. And then when we put the password in, and there it is by the way, because it's plain text, anybody sniffing the network or getting a hold of these packets would be able to determine what that password is because Telnet is plain text. So let's compare that to the capture for our SSH session. So for our SSH session, if we go to the beginning of that three-way handshake, right-click, and then from the drop-down, hover over follow, and once again click on TCP stream, this is a much different story. It did indicate some of the details regarding the version of SSH that was currently in play, as well as some of the protocols that were used for hashing and for encryption, but as far as the content, oh my goodness, there it is. And because of the encryption, we have some confidentiality or privacy regarding the passwords and the details and what was going on between the client and the SSH destination that the client was using. I'd like to clear the air about one thing right off the bat, and that is I have a lot of admiration and appreciation for the command line interface. And part of that might be because that's how I cut my teeth in working with networking back in the 80s. But something happened along the way where they got graphical user interfaces available for configuring things, and oftentimes wizards, where just a few clicks of the mouse could create dozens or hundreds of lines of code that could help facilitate the configuration of a network device. So with a big appreciation for the command line interface and its many use cases, I also want to point out that using a graphical user interface is very helpful in many situations. And most of our commercial grade network devices like switches and routers and firewalls have some type of both command line interface as well as some type of graphical user interface for managing that device. And if we have multiple devices from a single vendor, it's often possible to have some kind of enterprise management software that allows us to have a graphical user interface to both monitor and configure multiple network devices. And the graphical user interface is not going away anytime soon. And here's an example. In a VMware vSphere environment, we have lots of moving parts, a lot of cool parts, including some ESXi hosts here, here, and here, and we can manage them either via a command line interface. We also have the option of connecting to them using HTTPS for security and getting a graphical user interface independently. But even managing those independently, if we have lots of them, isn't very practical. So VMware, like other vendors, provides a centralized solution. VMware calls this centralized management vCenter, and they have an appliance called vCenter Server Appliance. So that administrators, we can connect to this management interface, and then the management appliance can reach out and deploy our configuration elements on the individual servers. But going back to our point of individual servers supporting HTTPS, let me give you an example of connecting to an individual ESXi host that's running hypervisor software to give you a taste of what that might look like. So here in a lab environment, I'm just opening a browser and I'm connecting out to https://192.168.1.101/UI, which is a specific management URL to manage the ESXi host. And because I just brought up the ESXi host, it's using a self-signed certificate. And so my browser is saying, whoa, warning, Will Robinson, I can't verify that signature on the digital certificate. And that's at least one of the problems that it's reporting right there. So for the purposes of the demo, I'm going to go ahead and click right here to continue to this website. It gives us the login screen for that specific ESXi host. So I'll go ahead and log in by supplying the username and password and clicking login. And that's taken us to the management interface right here for this specific ESXi host as part of a vSphere environment. Whenever we have data that's coursing through the veins of our networks or crossing other people's networks and we want to protect that data, we can do so by using cryptography and a feature called VPNs. And the two major categories are site-to-site. For example, we have a branch office out here, we have our headquarters location over here, and we want to create this logical secure path, this tunnel, this virtual private network between the two. And that way any traffic that's leaving the branch office that goes over the tunnel will be encrypted and protected until it reaches the other side. At that point, that traffic, those packets will be decrypted and then forwarded on to its final destination. The key is, it's protected as that traffic travels over the virtual private network between the two sites. Another option is a remote access VPN for an individual user. So this could be Bob, he could be at home on his computer or on his mobile device, and he could also build a virtual private network between his computing device and the other end of that VPN tunnel. And that's referred to as a remote access or a client-to-site virtual private network. There's also a couple of different flavors of virtual private networks we can implement using either SSL/TLS, which is the same technology we'd use when we're connecting to a secure web server. And when using SSL/TLS, the well-known port for HTTPS services is port 443 on TCP. And another protocol we could use for building VPNs, which is traditionally used for site-to-site VPNs, is IPsec. And IPsec has its own layer 4 protocol. It is protocol number 50. So it does not run on TCP, nor does it run on UDP. It has its own protocol number, protocol 50. Now, if we are using SSL/TLS with our VPNs, one challenge is that because it does use TCP, there's a little bit of overhead with all the acknowledgments and sequence numbers and so forth. So they came up with a compromise called DTLS, Datagram Transport Layer Security. And effectively what it does, it puts a wrapper, a UDP wrapper specifically, on the traffic as it's crossing over the VPN, and that way there's less overhead for the ongoing data going back and forth, which will have some higher efficiencies because of less overhead compared to using SSL/TLS. And before we roll out a virtual private network, for example, a site-to-site between the branch office and the headquarters site, we should identify a few things. The first question might be, what traffic do we want to protect and encrypt and send over the tunnel? So if over here on the left, we have the 10.1.0 network, and out here at the branch office, we have the 10.4.0 network. As part of our plan, we could say we want to encrypt and tunnel everything that's coming from the 10.1 network going to the 10.4 network. And because cryptography has several options available to us, we'd also want to identify what protocols do we want to use to encrypt the data, what protocols do we want to do for hashing to verify the data hasn't been modified or changed in transit, and what type of protocols do we want to use to authenticate. So if we decided that router 3 is going to be one end of the VPN tunnel and this router right here is going to be the other end. We're going to build a VPN tunnel across here. We'd configure both of these devices, in this case router 3 and this other router, and we'd tell router 3, anytime you see traffic going from 10.1.0 going to 10.4.0, go ahead and encrypt that traffic and ship it over to your peer, which is the other router over here. And the receiving router will decrypt that and forward the packets to their final destination. And on the flip side, this router over here would be trained that any traffic coming from 10.4.0 going to 10.1.0, when it sees that, it should be encrypted, wrapped up, and shipped over to the peer, in this case R3, who would decrypt it and then send it over to the final destination. And what I'd like to do is show you a packet capture of some traffic right here, which is pre-VPN, and then that same traffic as it's crossing the VPN tunnel. So here on the left, we have a packet that is sourced, if you take a look at the layer 3 information, sourced from the device at 10.1.0.11, destined for 10.4.0.4, and if we open up the details of this ICMP message, it's a ping request. So this is before R3 sees it. Now when R3 receives that packet, it takes a look at the source and destination and says, whoa, I've been trained to encrypt this and ship it over to my good buddy, my peer, at the other end of the VPN tunnel. And that's what we see over here on the right-hand side. It's been encrypted and then re-encapsulated into a new IP packet with all the original payload encrypted. So if we expand this, at layer 3, the source of this packet is R3's address of 67.A3.45.3, and the destination IP address is the other router at the branch office. And in my lab environment, I put that next router at .4. Also, if we expand the IP header here, and let me scooch this down just a little bit, this is also showing the IP header that the next protocol is encapsulating security payload, which is protocol 50. And that's the protocol we see right here, ESP. And all of this data here is the original IP packet with the original source and destination address at layer 3, and then the ICMP echo request. And all of that data is sitting as the ESP payload that we're looking at right here. So anybody who steals a copy of this packet as it's going over the VPN tunnel, because they don't have the keys to unlock it, it's just a bunch of ciphertext, a bunch of gobbledygook that they can't make sense of. And that's how we can keep our data confidential, by using a virtual private network and encrypting that data as it's being sent over the tunnel to the other side. Not too long ago, I was asked by a friend to help them with an issue they were having on their computer, so I connected remotely over to their computer using a remote desktop technology so I could see what they were seeing. So it's as if their computer screen was showing up not just on their computer, but also on mine, so I could take a look. Well, the good news about remote desktop protocols is that there's several of them out there. And one of those is RDP. It's the Remote Desktop Protocol, which is a protocol created by Microsoft and available on many of their platforms that allows you and I to sit at this computer, for example, and then request a remote desktop session to another computer, maybe this guy right here, or perhaps a server. And while that remote desktop session is in place, our screen is reflecting what's on the actual server screen, and when we type in keystrokes and use the mouse, all that activity is being shipped over to that remote system and being implemented there. And RDP uses a combination of TCP and UDP ports, and the major port is 3389 that's assigned to Remote Desktop Protocol. Another remote desktop option is VNC, which stands for Virtual Network Computing, and that uses ports in the range of 5900. And if we want to use VNC, what we'd do is we'd go to the device where we want to use it, we'd install the VNC server function, and then from the client we install the VNC client function, and then reach out and connect to the server piece to get remote desktop access to that remote device. Another popular option is VDI, which stands for Virtual Desktop Infrastructure, which is once again about getting remote desktops. So if we have a virtualized environment with hundreds of VMs, maybe we want our users at these computers to remotely connect to those VMs, and then those will be their workstations, meaning all these virtual machines that are running in our hypervisor environment. So with VDI, we'd have some method of doing remote desktop connectivity to those devices. A popular option is called PC over IP, which allows us to get a remote desktop, and PC over IP uses port 4172 along with some others. So as an example, let's go ahead and connect to a computer, this guy right here, that's at .120 on the 192.168.1 network. And let's use RDP because the remote desktop functionality is already built into this Windows computer. So if it's enabled on this device at .120 from another computer, we can use a remote desktop protocol application. to connect to the .120 device, authenticate, and then have remote desktop access courtesy of RDP. So from this computer, we're going to reach out and connect over to the device at .120. So to do that, we'll click on the Windows icon, we'll type in remote, and the best match that comes up here is remote desktop connection, which is built into this operating system from Microsoft. And then we'll go ahead and put in the IP address of the device we're going to connect to, which is 192.168.1.120. And with that in place, we'll go ahead and click on connect. It's asking us to authenticate at that remote device, so I'll supply the password and click on OK. And we are now connected to that remote machine. So this is the desktop of that remote machine. As we move our mouse here, all that activity is effectively being transported via RDP over to this remote machine. This is a visual indicator up here indicating where we're connected to. And if we want to close our session, we could just click on the little X here. That would close our remote desktop session. We'll click on OK. And that takes us back to our original computer. If we were to take a look at a packet capture of that traffic, here we have an initial three-way handshake. There's our SYN, there's our SYNAC, and our acknowledgement, going from .100, which is where we started from, going over to the .120 device right here, to the well-known port of 3389 associated with remote desktop protocol. So in the background, the three-way handshake proceeded, we authenticated, and then we're given remote access via RDP to that system. I'd like you to consider with me the consequences or what happens after a network device goes down or fails. Now, besides the inconvenience it's going to cause for the users who are relying on that device, such as a router or a switch, if we are going to replace that device and we get a new physical unit and we put it in place, we're going to need the old configuration so we can put that configuration on the new device. And one handy way of having those files saved and ready to go is to have them backed up or stored on some type of a file system that's available from that network device. So let's imagine that it's our router that has failed, and so we put a new physical router in its place, and this is our file server. Now hopefully we've taken the time before the failure to have backed up the configuration over to the server, and depending on the gear that we're using, there are several different types of protocols that we can use to store and retrieve files on our network. And those include FTP, the file transfer protocol. Then we have FTPS, which is FTP with the benefits of SSL/TLS for security. We have SFTP, which stands for Secure FTP, which leverages SSH to make the FTP session secure. And then we have Trivial File Transfer Protocol, which uses UDP and is very insecure. However, because it's using UDP, there's not a lot of overhead at the transport layer, and it may come in handy if we need to have an initial image or something moved over to a router that doesn't contain sensitive or confidential information, like the raw operating system for a router or for a switch. Another time that can come in handy is if we're doing an update or an upgrade of the operating system or a configuration and we want to copy it over. So let's imagine it's 11 p.m. We're in a change control window. We've got authorization to update the operating system on this router. So with the connection to this router, we have that router copy the image or the upgrade from the file server over to the router. And then as part of making that operating system run on this device, we need to reboot the router. So we issue the reboot command, and then we wait, and we just hope it comes back. And see, the problem is when this device is rebooting, it doesn't know how to communicate anymore out of its routed interfaces. And so if we're connecting to it over one of its routed interfaces, we are basically out of luck until this thing successfully reboots and then allows traffic in and out of those interfaces once again. And the question may come up, well, how do we verify while this thing is rebooting that it's actually working successfully? And one option is we could get a console cable and connect to the console port on the router. And let's say it's in the wiring closet. So we'd be physically in the wiring closet with our PC with a console cable connected to the console port. Then we could see all the messages and information as it's booting up. Another option, if we didn't want to have a PC that was physically right there, what we could do is we could have a modem, a modulator, demodulator connected to some kind of a phone network. Then instead of connecting ourselves directly to the console port, we could connect the modem to what's known as an auxiliary port. It's also possible we could connect to the console port with the modem as well. But if the router has an auxiliary port, it's intended for that purpose. So then on our PC, we would dial up, connect to that modem, which would then give us connectivity to that port. And that would be considered an out-of-band management path for us to manage that router. Because we're not going through the traditional Ethernet network to access the device, we're coming in via another path, through this auxiliary port and the associated modem. But here's one of the challenges. If we have multiple devices and we want either console or auxiliary access to most of them, we don't want to have individual modems on every single device. And here's the solution to that problem. We get a box that has a unique interface that supports, in this case, it's 8 serial interfaces, 8 cables coming out of this one connector. And out of those 8 connections, we can put one of them into the console port for this device. We can take another one of those cables and connect it to the console port on this device. And if there's more than 8 devices that we need console access to, in this case, we could go ahead and get another octal cable right here and continue on our journey. So what we would do is we'd connect to this bottom box, and then we'd use a process called reverse telnet to establish console sessions through these serial cable interfaces to the console ports of the other devices in that wiring closet or in that area, which would include connecting to the console port of our router and the console port of switch 2 and the console port of switch 1, possibly the console port on an access point, or anything else that supported a console port and was physically in that same area where these cables would reach. Then we'd have one connection to this bottom box, which would facilitate our console connections to the other devices. And this bottom device here is actually an older Cisco router, and this bottom router could be referred to as a console router or a terminal server, for the purpose of making one connection to it and then getting access through its serial cables to the console ports of the other devices. And the goal of that is that would provide us out-of-band management, and that out-of-band management gives us access to those console ports regardless of whether or not the Ethernet interfaces on those networking devices are currently active.
Thanks for watching our second, and press the button below, like, subscribe, and bell icon.